Hey, good morning, and this is Dr. Joel Shertok, President of Process Industries Consultants, a chemical engineering consultancy located in Newark, Delaware. Today, I'd like to get a little bit more in the weeds. We have discussed in my previous podcasts the specialty chemical industry and my perspective, and also my perspective of how the CPI, chemical process industries, have changed in the 50 years that I've been working. But today, I'd like to talk a little bit more about technology. If you're a vice president or manager or director of operations in a CPI or materials or biotech company, you are held responsible for profitability. Not the chief financial officer, he's just the bean counter. But you, every day, the decisions that you make impact how that plant runs and how the profitability and margins of that plant come out at the end of the day or the end of the week. And effectively, you have a loaded gun against your head every day, and having been in operations, I totally appreciate that. Everybody looks at you and expects the daily miracle. And it's always a case of, what have you done for me lately? So I'd like to take a little closer look at a way of quantifying opportunities and perhaps a little look at where the opportunities might lie in your plant. So I'd like to take you back to the dark, distant days of the early 1980s, and a man who worked for ITT, International Telephone and Telegraph, now defunct, named Philip Crosby. Crosby was the quality manager of ITT. And this was just before the Japanese quality revolution hit the United States industry. So he was kind of a voice crying out in the dark. And he had this problem. How did he get senior management to buy into the concept of quality, which is kind of whiffy and qualitative, and everybody thought they knew what it was, and really nobody did. And he had this incredibly inspired idea. He called it the Price of Non-Conformance, or Ponc. We used to say, let's suppose you're running a plant with $100 million a year revenue, and you're having losses of 1% of your gross margin. You are basically looking at $1 million down the drain. $1 million that belongs in your pocket, or more precisely, the company's pocket. So what Crosby did is, okay, if I have that $1 million, how do I divide it up? How do I quantify it so that it makes sense to bean counters, financial people, engineers, et cetera, et cetera? And as I said, he came up with the concept of the price of non-conformance, which is to say putting a dollar value on every inefficiency that a unit would have, whether it's a chemical plant, an advertising agency, anywhere where there's inefficiency, there's a price of non-conformance. It's money that goes down the drain. Well, great. So he had the concept. What do you do with it? Well, by extreme luck, one day, he was about to get on the elevator to go to his office at the ITT headquarters in New York. And who should get on the elevator with him but the CEO of ITT, Hal Janine. ITT in the 1980s was the epitome of the two-fisted conglomerate. Tons of different businesses, totally unrelated. And the theory was that if one business did bad one quarter, the other business would do good and you'd come out ahead. That's sort of gone out of vogue right now, and it's more or less stick to your knitting. But in the 80s, that was the model that everybody followed. And Hal Janine, CEO, was the two-fisted proponent of this philosophy. He was an incredibly tough guy. Yeah, this before managers went in for touchy-feely sort of stuff. So he and Phil Crosby got on the elevator together. And Crosby saw his opportunity. And he said, Mr. Janine, my name is Phil Crosby. I head your quality department. And you know that the non-conformances in your company are costing you tens of millions of dollars a year. Can I talk to you about it in more detail? And what Phil did is he created the elevator speech. That was the first elevator speech in corporate history. And it worked. Janine, in that 15, 20-second intro, was intrigued, invited Crosby to his office, and the rest is history. Crosby turned it into a very lucrative business. He founded Phil Crosby Institute, in which he promulgated this concept of Ponc, And I was fortunate enough as a Union Carbide employee to be trained as a Philip Crosby instructor, which is how I became familiar with the concept. So, Mr. Operations, how can you use this? Your unit, facility, plant, whatever, has a price of non-conformance. Your price of non-conformance is costing you gross margin every day. Where do you look? How do you quantify? What do you do? Well, my suggestion, based on my experience, is anywhere you have a reactor or reaction, that is the first place you look for a price of non-conformance. Can you quantify your reactions of inefficiency? Can you quantify raw materials going in, raw materials product going out? Any deviation away from 100% is effectively a price of non-conformance. Now, we all know that no reaction is 100% efficient. Absolutely cannot happen. There's always side products. But your responsibility as an operations guy is to say, hey, let me look at my reaction step and see if there's something there that I can look at and maybe make more efficient. So what you need to do is to have your engineers, have your R&D department, look at that reaction step and say, guys, here's the issue. I know I have a price of non-conformance. It's probably in the $1 million a year, maybe even more. How can I get this reaction step to be more efficient and to make less byproducts? And why do I say that? In most chemical units, it's the reaction step that sets the stage. If that's done well, your separations and your processing and et cetera, becomes much easier. If you have issues in your reaction step, you're playing catch up for the rest of your plant. Your separations unit is labeling under a strain. Your separations unit is not doing as well as it could. All the post-reaction processes are laboring under a bad reaction, or not a reaction that's not as good as it could be. So what do? Well, it's very simple and not so simple. What's going in? What's coming out? I'll give you an example. One of my very first assignments as a chemical engineer in R&D was looking at Union Carbide's phenylacetone plant at Ponc, Puerto Rico. And it's a very straightforward reaction. You bubble air through cumene at maybe 90, 95 degrees C, and that causes a reaction that forms cumene hydroperoxide. Cumene hydroperoxide is broken down to phenol and acetone, which is then purified in a somewhat complex distillation train. Problem is, there's two modes of reaction that sometimes people don't quite understand. There's a kinetic mode in which reaction kinetics play the predominant role, and there's a mass transfer regime where mass transfer of oxygen from air across the interface into cumene sets the stage. And so intuitively you say, well, I want to get more phenylacetone out of my unit. Oh, I'll crank up the temperature. Seems intuitive, right? Trouble is that if you are in the kinetic regime, you're absolutely right. More temperature, faster reaction, more product. But if you're in the mass transfer regime, cranking up temperature is not going to help you, because what's governing that reaction is mass transfer. Oxygen getting into cumene and reacting. You could crank up the temperature as much as you like. Yes, you'll probably increase mass transfer, but not as much as making byproducts, because your reaction between oxygen and cumene, it's being controlled by mass transfer. The more severe your reaction, the more tars, impurities, and garbage you're going to make. That's going to cost you product, efficiency, and ultimately cost. So my job was to understand the different regimes and understand how to optimize the temperature profile and oxygen flow rate so that each reactor was always in the kinetic regime. And I required an optimization program, modeling the mass transfer, modeling the kinetics. And this is the dark days when people use punch cards, not pre-canned programs. So everything was done from scratch. But it was successful. We raised the efficiency of the cumene phenol plant, which made 180 million pounds of phenol per year. And we raised the efficiency from 96% to 98% just by manipulating the kinetic and mass transfer regimes. So your price of non-conformance was reduced with zero capital investment, no real change, just the knowledge of how the various process parameters interacted with each other. And to you, Mr. Operations Manager, this is the key to your kingdom. You need to understand how your system works. You need to understand all the regimes. And you need to understand how your reaction train can be optimized to give you the best possible efficiency. So what happens next? Well, now let's suppose you've got your reaction straightened out. Wonderful. You now have to, there's another reaction step possibly. In case of cumene phenol, there's a reaction with SO2 that causes the cumene hydroperoxide to decompose. Again, that has to be done correctly as well. Too much SO2 causes a severe exotherm. Severe exotherm causes side reactions. Side reactions, TARs, stuff you don't want. Uh-oh, uh-oh, uh-oh. So there's another reaction that needs to be understood. The tendency is, let's crank the temperature, let's put in more SO2, ain't gonna work. Ain't gonna work, gonna give you more garbage out the other end, and increased price of non-conformance. So again, there's another reaction step that you have to understand, that your staff has to understand to reduce your price of non-conformance. Typically then, okay, we're going to distillation. Now distillation, fairly well understood, right? But there's always complications. There's always complications. Vacuum costs money. And obviously, since you're dealing with high boilers, you have to run these columns under vacuum. You have to run possibly your condenser at refrigeration, possibly run your reboilers using high pressure steam. And all these things have to be balanced so that your price of non-conformance, be it electricity costs, cooling costs, or TARs that you make during distillation, are minimized. And that requires understanding of all these trade-offs. If you run your reboiler too hot, you cause polymerization. If you run your reflux too low, you're going to lose product. Run your reflux too high, going to cost you money in refrigeration costs. If you're not careful, you'll take all the good things you did in reaction and just mess them up during distillation. And again, what you need is a well-trained staff that understands how all these different parameters interact so that you can optimize your system. Now what's next? Well, you made your material, you've got your phenol, you've got your acetone, you have your acetophenone, you have your alpha-methylstyrene. Again, your next challenge is, how do I package this? How do I ship this? How do I make sure that I don't take all the good things I've done and mess them up? And this is a matter of good plant hygiene. Your pipes have to be clean, your tanks have to be clean, your level indicators in your tanks have to actually be working. And let me give you a story. Once upon a time, we were making a special grade of caprolactone for a very, very key customer. They used it for automobile coatings, and therefore the caprolactone had to be absolutely pristine. So the R&D staff, with which I was in charge of, developed this process that made really great caprolactone. So we signed, a production engineer was assigned to us, and he reserved a special tank for us in the tank farm that would receive this ultra-pure caprolactone. And the plant questioned this poor guy, and they said, are you absolutely sure this tank is pristine and blah, blah, and ready to receive it? Because the slightest bit of contamination, and that's the end of your product. He said, absolutely, it's pristine, ready to go. Wonderful, wonderful. So began the process. Caprolactone came out the product line, and it was looking really great, put into the tank. But there was a problem. As we put more and more and more caprolactone into the tank, the level indicator didn't move. didn't move. So after about 20 minutes, that didn't, something's wrong. That level should be going up pretty fast. So I called the instrument repairman of the plant, and he said, could you take a look at this level? Something looked fishy. And he came over and made an adjustment, and the tank level went from 0 to 50%, which was totally impossible. We hadn't put that much stuff in there. So what had happened? The engineer didn't check the tank visually. He depended on the level indicator. And since the level indicator said 0, he said, hey, it's 0. We're in great shape. It turns out the level indicator was broken, and the tank was about a quarter full with bad standard caprolactone. So what had happened was we took really pristine caprolactone, mixed it with bad caprolactone, and guess what? We got a bad product. Again, like I said, you've got to take care all through your process. Now, the engineer got into something of a serious mess because the amount of money down the drain was a real serious price of non-conformance. But we went down to the plant about 2 months later and did the run again, and this time the engineer in charge physically inspected that tank to make sure it was absolutely empty. And it's this sort of industrial hygiene that's vital to you as an operations manager to ascertain, make sure, program, any way you want to do it, to prevent unpleasant surprises like that. So what I say is, by understanding your reaction, by understanding your distillation, by understanding something as mundane as product storage, you can keep your price of non-conformance to a minimum. You can take that $1 million of lost profitability and put that back in the plant's profits. Thank you very much. We'll continue this in another podcast.